Section 5, talking about random variables. So what we want to do is we want to take the probability rules that we established in the previous section, and we want to narrow them in a little bit on why they're of interest to us in this course. So we'll start with the concept of a random variable. A random variable, not to put too fine a point on it, is a variable that's random. So randomness we've talked about. What's a variable? Well, a variable can be one of several numbers. So in other words, a random variable can be one of many numbers, but which one it's going to be is random. A random variable is a variable that assumes one of several numbers as a result of a random phenomenon. So in other words, you do something random and you get a number. Now this is not a major limitation on anything we've previously talked about, it's just that our perspective is numbers. For instance, if you flip a coin, then you could somewhat sarcastically say, how many heads do you get? Well, either 0 or 1. But you see, our focus is on numbers. So the easiest example, the archetypal example of a random variable would be to roll a die. You roll a die and you get a 1, a 2, a 3, a 4, a 5, or a 6. And if it's a fair die, they're all equally likely. Another example that we've talked about in the past is that you can spin our spinner. Of course, it can be any kind of random number generator, but the example we did in class several times was to pick a random real number between 0 and 4. We had our circular spinner with this being 0, this being 1, this being 2, this being 3, and it was infinitely sharp, and we give it a good spin, and it could land at any number between 0 and 4. 0 point anything, or 1 point anything, or 2 point anything, or 3 point anything. Of course, there's a very big difference, of course, between being any real number between 0 and 4, an infinity of possibilities, a very infinity of possibilities, versus being one of 6 possibilities. So we can make the distinction between a discrete random variable and a continuous random variable. Let's see, I didn't actually define the latter here. I think I left it off for the next section. But a discrete random variable, for our purposes in this course, can be one of a finite number of possible values. In other words, a discrete random variable can be this number, or this number, or this number, or this number, or this number, full stop. Whereas a continuous random variable can be any number, any real number in an interval. So rolling a die would be an example of a discrete random variable because there's a finite number of numbers it can be, 6. Whereas spinning our spinner, picking a random real number between 0 and 4 in the quote obvious unquote way, would be an example of a continuous random variable because you could be literally any number between 0 and 4. Now we'll talk a great deal more about this as we go on, but bear in mind in the real world there is always going to be gray area, right? The theoretical distinction here is between a discrete random variable which has a finite number of possible values and a continuous random variable which can be any number in an interval. We'll talk more about those in section 6. However, the practical distinction is as follows. In the end, it always comes down to how you're going to treat it. As I've said before, there's always such a thing as close enough. So for instance, if you've got 20 people in the room and you pick somebody at random and you measure them, then what number of inches tall they are that you get is an example of a discrete random variable, right? You can get the height of the first person or the second person or the third person or the 19th person or the 20th person, right? And presumably, if you're equally likely to pick any of the 20 people, then the probability of any particular height is a 20th. Unless, of course, there's repeats, If there's 2 people that are the same height, then that height has probability 2 20ths, and so forth and so on. However, if you pick the height of somebody from the world, then you can effectively get any height between the shortest person in the world and the tallest person in the world. You see what I mean? Everything I just said in the first example is technically true. Let's say that there's 6 billion people in the world. That's probably a little bit on the small side, but for the sake of argument. Oh, on a totally unrelated note, when I was born, there were about 3 billion people in the world. So it's doubled in the time that I've been alive, right? So I really don't know what the heck Thanos was thinking. He seems to have been under the impression. In the end, he made the same mistake that General Zod made in Man of Steel. He forgot that people can make more people. You get rid of half the people in the world, and 50 years later, you've got to do exactly the same thing again. So it was always a stupid idea. Anyway, notwithstanding, let's say that there's 6 billion people in the world, and well, then everything I said about the 20 is still technically true, right? If I pick somebody from, no, uh, bearing in mind, of course, there's going to be repeats, but along these lines, if you pick somebody from the world, then you could get one of 6 billion possible heights, maximum, because there's going to be repeats, right? So technically, yes, if you pick somebody from the world and measure them, there are a finite number of heights you could get. But, of course, you wouldn't want to work it out, right? If you had 20 people, you could write down the probability of this height, the probability of this height, the probability of this height, the probability of the 20th height. It's very atomic, you know? Individual possibilities, each with their own tiny little... individual possibilities, each with their own relative weight. Like rolling the die, you know? A sixth, a sixth, a sixth, a sixth, a sixth, a sixth. But nobody in their right mind would want to write down all 6 billion possible heights you could get and the probability of each, right? So it is technically a discrete random variable because there are technically a finite number of heights you could get. But it is also close enough to true to say that you can get any height between the shortest person in the world and the tallest person in the world, right? Can you get somebody who is pi feet tall, 3.14159, did it at no pattern forever? No, of course not. That doesn't make sense. You can't measure people with infinite precision. Even if you could, they couldn't be an irrational height, presumably. And of course, there is an infinite number of numbers. There's an infinite number of real numbers between the shortest height in the world and the tallest height in the world. So it isn't technically true that you can get any real number in there, but it's close enough, right? It's close enough to true to say that you can get any height between the shortest person in the world and the tallest person in the world. So you see what I mean? In the real world, the practical distinction is between a variable where you can actually write down every possibility in, let's say, column form here, ending with the last one, and a variable where you can effectively be any real number between this one and this one. I'll give you another example. If you flip a coin 3 times, you can get 0 or 1 or 2 or 3 heads. And it matters a great deal whether you get 1 head or 2 head. We've talked about this a little bit in the past. If you flip a coin 3 times, then getting less than 2 heads, that is 0 or 1, is very much a different thing from getting at most 2 heads, 0 or 1 or 2. Which is to say, you know, the probability of 2 heads exactly is not insignificant, you know? Probability of 0 heads, probability of 1 heads, probability of 2 heads, probability of 3 heads, 4 numbers, each of them relatively heavy, you know? Those probabilities are not insignificant, and those 4 different numbers add up to 1. But let's say you flip a coin 4,000 times. Well, it is still technically a discrete random variable, and we could still technically make a chart for it, right? 0 heads, probability of that. 1 head, probability of that. 2 heads, probability of that. 4,000 columns later. 3,999 heads, probability of that. 4,000 heads, probability of that. But you would never want to look at such a chart, and it would be meaningless in any case, right? Most of those probabilities are going to be 0.00000 something. They're insignificant. And again, let's take that question we were looking at a second ago. If you flip a coin 4,000 times, the probability that you get less than 783 heads, the probability that you get at most 783 heads. Well, again, individual possibilities are insignificant. The presence or absence of 783 itself adds or takes away virtually nothing, right? In a word, it's much smoother. It's not so jaggedy as what we're seeing for small numbers of repeats. So in the real world, there's such a thing as close enough. If you flip a coin 3 times, it matters a great deal whether you get 1 head or 2 heads. If you flip a coin 4,000 times, nobody cares whether you got 783 heads or 784 heads. They're insignificant. They're practically the same. So in the real world, there's such a thing as close enough. For all practical intents and purposes, if you flip a coin 4,000 times, you can get any number of heads between 0 and 4,000. Is that true? Can you get 1,200.5 heads? No, of course you can't, but nobody cares whether you get 1,200 or 1,201. It's an insignificant segue. So in the real world, there's such a thing as close enough to any real number between starting point and stopping point. So again, the theoretical distinction is between a finite number of possible values and any real number in an interval. However, there are very few random phenomena where you can literally get any real number between this and this. Even our infinitely sharp spinner is just a conceit, right? You couldn't make one in the real world. And you couldn't observe the outcomes of it even if you could. Our eyes can't view things on the infinitely microscopic level. So in the real world, there's such a thing as close enough. The practical distinction is between something where you or I would want to write down all of the columns. How many columns do you want to deal with at worst? 30? Maybe 40 if you're feeling very bored? Versus something where you've got so many columns that you may as well say that you can get anything between the first one and the last one. So don't be too high-minded about it, and remember that these are somewhat artificial distinctions. There are things we're not going to talk about in this course. Some of them are in the book if you're interested. There are things we're not going to talk about in this course that don't technically fit either one of these. For instance, how many flips of a coin does it take to get a head? 1 or 2 or 3 or 4 or 5 or 6 forever and ever and ever isn't really either one of the things that I've just talked about. But you can't add up an infinite number of things without calculus, so we're not going to talk really about situations like that. The book will give you some formulas for them if you're interested. For our purposes, we have a discrete random variable which can either be this or this or this or this or this, full stop, or a continuous random variable which can be any number in an interval. Now let's back up a bit. From a probability perspective, pretty much all of the things we talked about in section 3 were continuous random variables. Pick a random real number between 5 and 21. Well, it's just another example, right? 5 point anything or 6 point anything or 7 point anything, so on and so on. It's what, 16 long, whatever. Average 2 random numbers between 0 and 1. Like I said, this is a triangular type thing. They tell you that. But you can get any real number between, you can get 0 point anything, so it's another continuous random variable. Pregnancy length, well, effectively you can get any pregnancy length between the shortest pregnancy there's ever been and the longest pregnancy there's ever been. Now, can you measure pregnancies with infinite precision? No, of course not. There's always a fudge factor. But let's put it this way, you can do a lot better than a whole day, right? it's meaningful to say that a pregnancy is 266.231 days, right? That probably gets it down to a couple of minutes. So that's meaningful. There's always going to be fudge factors, but you wouldn't want to treat it like a discrete random variable where you have every possible pregnancy length and its atomic probability. You'd have to use areas for such a thing. Doesn't matter whether it's rectangular, number 1, or triangle, number 2, or normal shaped, bell shaped, all the rest of these. SAT scores, well, again, approximately normal shaped, that's all you need to know. If you're using areas like that to compute probability, then you're talking about a continuous random variable. For all practical intents and purposes, you can get any SAT score between the lowest one and the highest one, 800. Can you get 500.27? No, of course not. Well, not after they report the scores anyway. And there's only a finite number of questions, of course, so you're not going to have scores that are quite that microscopic. But nevertheless, you can be hundreds of different things. It is close enough to say that you can be any number in there. And so on and so on. GRE scores, much the same thing. Potassium levels in the blood. I mean, I don't know how microscopically they can be measured, but, presumably it could be 3.521 something, right? So effectively, you can be any potassium level in the blood between the smallest possible, 0 I suppose, and the biggest possible, whatever would result in death, presumably. Batting average is much the same thing. Presumably they don't go beyond 3 decimal places, but that's a whole lot of things between 0 and 1, close enough to a continuous random variable. And so on and so on and so on. Snow tire tread lives. You could probably get a little bit more, even if you were doing to the nearest mile, that's still a lot of numbers, right? The tire that lasts the shortest number of miles, the tire that lasts the longest number of miles, even if you had to round it to the nearest mile, that's still a whole lot of numbers that it could be, right? And of course, you could peg it better than the nearest mile, right? I mean, you could literally peg it to one roll of the tire itself, one diameter, right? 2-3 feet. So that's a whole lot of possible tire tread lives. It's close enough to a continuous random variable, and so on and so on. Kindergartner heights can't be measured with infinite precision, but close enough. Same with temperatures, So, where was I here? Okay, so here we go. So we'll talk more about continuous random variables in the next section, but the bottom line is there's not much to say about them in a course like this that we haven't already said. You use areas to compute probabilities for a continuous random variable because the probability of exactly anything is 0, as we've seen. Whether it's rectangular shaped or bell shaped or any other shape. Now, there's not a lot of areas you can do by hand, so theoretically that could result in a lot of calculus to do things like that. So we're obviously not going to get into that too much. In a higher level statistics course, you would. As we've already seen, if it's anything much more complicated than a rectangle, we're going to want to use charts to find those probabilities. So I'll tie all that together for you in section 6. But we've basically said all we're ever going to say about how to compute probabilities of continuous random variables. As for discrete random variables, where you have an actual writable probability of particular possibility number 1, and so on and so on, well, you could put them in these probability charts, right? So it could be something as simple as a fair die. A word on notations here. We use capital X for the random variable itself, the concept of the random thing you're doing. Capital for the concept, as I said, lowercase for the particular possibility. So x sub 1 represents the first number that random variable could be. X sub 2 represents the next number that the random variable could be. X sub n represents the last number that the random variable could be. By the way, for the future, because this will get a little confusing, notice that there is a sleight of hand here. up till now, we've used n to represent the number of pieces of data. But now we're not talking about data necessarily any longer. The concept of a fair die makes sense whether you ever roll it or not. So now we're using n in a different way. Now we're using n to represent the number of possible things x can be. Remember that for the future, because on a separate page here, I think it's this one, we'll kind of bring these concepts together. So things to be aware of. We're using n for the number of columns. We're using n for the number of different things the variable could be, with the understanding that it's finite enough that we could actually list them off. So then lowercase x sub 1 for the first thing x could be, lowercase p1 for its probability, and so on and so on. Now let me just say that there's nothing I'm going to do with these charts that presumes that the numbers are in order. However, they always will be. It just looks nice if they're in order, but strictly speaking, nothing I am going to do with these charts will presume that they're in order. So x1, the first thing that catches your eye that x could be, x2, the second thing that catches your eye that x could be, and so on. It's just common sense to list them in ascending order, but strictly speaking, we're never going to use the fact that they're in order. It does make the pictures comprehensible, but no, in no other way. So we're not going to computationally ever use the fact that the numbers are in order. So then a simple example, well, simple examples are deceptive because in this case all the p's are the same number, but the concept of a fair die. So it can be 1 or 2 or 3 or 4 or 5 or 6, and the probabilities of a fair die are 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. Now bear in mind, it doesn't necessarily have to be a fair die. These could be 6 different numbers as long as they add up to 1, right? Exactly one of the numbers will occur, no more, no less, when you perform the random phenomenon x. So of course they've got to add up to 1. You can't miss anything and you can't double count anything. They've got to add up to 1. But it could theoretically be some other combination if a 3 were more likely and a 5 were less likely, as long as they add up to 1. So it's an easy example, but it's a deceptive one. x1 is 1, x2 is 2, x3 is 3, x6 is 6. Well, it's deceptive for that reason. That subscript happens to be this, and it's deceptive because all the probabilities are the same. Now, if that confuses you, bear in mind that you could take a fair die and physically paint over with any 6 numbers that you like, right? You could put 23 on one side and 84 on another and 7.5 on the third side and so on and so on and so on, right? But visually speaking, we've got all probabilities the same and the possibilities are equally spaced, right? Go over 1, go over 1, go over 1, go over 1, go over 1. So if we represent it in visual form with a probability histogram, then it's going to look something like this, right? Now, this is not exactly what I'm looking for. It's just the closest thing that I have on hand here. 6 bars, all the same height, that height being 1/6, right? So a bar for 1, bar for 2, bar for 3, bar for 4, bar for 5, bar for 6. The scale leaves a little to be desired, as I said, and we're not looking at this vertical scale at all. This is a data example. We'll talk more about that in a future section. But if you roll, the concept of rolling a fair die will result in the probability of a 1 being height 1/6, probability of a 2 being height 1/6, and so on and so on and so on. This is data, so it's not perfect, but 6 bars, all of the same height. We talked about this a little bit in section 3, right? But we did it from a data perspective. As a probability picture, 6 bars, equally spaced, all of height 1/6 is the probability histogram way of displaying this. Now a word on probability histograms. A probability histogram is just an alternate viewpoint on any other histogram. I think this makes the point, right? Let's pretend that this height is 1/6, not 5,000. Let's make it a relative frequency histogram here. So if I've got 6 bars, 1, 2, bar 1, bar 2, bar 3, bar 4, bar 5, bar 6, I mean, for the possibility. Die can land 1, die can land 2, die can land 3, 4, 5, 6, and they've all got height 1/6. Then I can visualize this die landing 1 being of height 1/6. I can visualize it as the probability that the die will land 1 the next time. Or I can visualize it kind of the way I'm doing in this actual picture, which is that if I roll it many, many times, probably about 1/6 of them will be 1s. Or I can say that it represents the fact that 1/6 of all possible rolls of the die will be 1. Sound familiar? It's exactly what we talked about in the previous section, the 3 different perspectives on probability. The 1/6 height of this bar, or if you prefer, the 1/6 of the total area in this picture, represents the fact that there's a 1/6 chance of a 1. Probably 1/6 of many rolls will be about 1. Probably about 1/6 of many rolls will be a 1. If I roll it many, many times, probably about 1/6 of them will be 1s. Many, probably, about. Vague. Still the best way of thinking about it. Or number 3, 1/6 of all possible rolls will be 1, which is the most technically accurate way of thinking about it, but it's a little hard to wrap your mind around, right? So there's a simple example, but again, it's deceptively simple because the actual notations are the same as the possibilities, and because all the p's are the same. It's a simple example. Let's take a more complicated example and see how we can use our probability rules from the previous section. Let's say that 10% of people are left-handed for the sake of argument, and by people I mean all the people in the world you could possibly pick from, all the people in all of time and space you could possibly pick from. Whether it's finite or not, it's effectively infinite, billions and billions. A lot more, orders of magnitude more than we're ever going to pick. That's important. So that like picking 2 or 3 cards out of hundreds of cards, you effectively have a 10% chance of getting somebody who's left-handed, whether you put back or not. Let me say that again. We are never, in anything that follows here, going to take any kind of noticeable bite out of billions and billions of people. So whether you put them back or not, every time you go to pick again, you have close enough to a 10% chance of a left-handed person. In other words, the picks are effectively independent, like our example with the picking 2 cards from 5,200 cards. So example 1, we'll pick one person at random, and as I said before, somewhat sarcastically, I will pick a person from the world and count the number of left-handed people I get. Well, if he's not left-handed, I get 0 left-handed people, and if he is left-handed, I'll get 1 left-handed person. That may strike you as a little bit sarcastic, but why not? It's a good way of looking at it for where we're going. So then the probability that you get a right-handed person, that is 0 left-handed people, is 0.9. And the probability that you get 1 left-handed person, that is that you get 1, is 0.1, right? So our probability histogram looks something like this. 0, 1, height 0.9, height 0.1. Already you see it's a little right skewed. It's only 2 bars, but clearly it's not symmetric, right? It's highly, you can see from the picture that you're much more likely to get height 0. You are to get 0 left-handed people than you are to get 1 left-handed person. And I think that's mostly common sense, right? And let me stress, I've made this point in the past, these widths should be the same, right? Because human beings don't see height in a situation like this. They see area. So you want to have a standard width going on here so that height and area will both give you the same impressions. Okay, so, well, the 10% of people left-handed goes all the way down, but let's say that you pick 2 people at random. Now again, remember we have effective independence. One person taken to one side so that they're out of the mix, whether they're left-handed or not, you've still got billions and billions left to pick from, right? So you have effectively made no dent whatsoever in what's out there. So every time we go to pick, you have a 0.1 chance of a left-handed person and a 0.9 chance of a right-handed person, regardless of what you've taken away. Now, if we pick 3 billion people, that's no longer true, of course. We could take away all the left-handed ones or none of them. But you would never do that, of course. What we're picking never takes any noticeable bite out of what we're picking from. And why that is, we've talked about at the end of the previous section. You wouldn't be picking if that were the case. So now if you pick 2 people, you can get 0 left-handed people or 1 or 2. And you work it out using our and or principles. Now, as we've already begun to see from practicing the problems in the previous section, right? The way that this generally plays out for us is that the and principle has to do with a way of achieving your result. A way of achieving your result. This has to happen, and this has to happen, and this has to happen to achieve your result. And then the or principle has to do with combining different ways of achieving your result. You achieve your result if this happens or if this happens. So we use the and principle first to figure out the probability of a particular x, and then of a particular way of achieving our result, and then we use the or principle to put them together. I'll show you what I mean. But of course, there's no room for doubt on how you get 0 left-handed people. The first one has to be right-handed, and the second one has to be right-handed. Now remember, the slots are effectively independent, right? So you can just multiply. The probability that the first person is right-handed and the second person is right-handed. Well, the second person has a 0.9 chance of being right-handed regardless of what's in that first slot. Independent. Multiply. So 0.9 times 0.9. 0.81. And there it is. This is height 0.81, and of course here it is in chart form. As for 2, you've got to get a left-handed person followed by a left-handed person. And again, they're effectively independent picks, so we can multiply them. There's a 0.1 probability that the first person is left-handed. Regardless of what you've taken away, there's close enough to a 0.1 probability that the second person is left-handed. And by the way, if that's really going to bother you, let's say that you're not picking from 6 billion people. Let's say that you're picking from all people there could possibly ever be based on biology. Something that's theoretically infinite. But picking from 6 billion is close enough to picking from theoretically infinite. Now what about, so here it is, 0.01. So that, of course, is a typo, which is not going to be fixed anytime soon. But I'm just making a note. Errata again. That's 0.01. Sorry about that. There's always going to be typos. So what about 1? Now this is where, well, of course, here it is. Given that this is 0.81 height, 0.01 is going to be practically invisible, right? It's literally, this bar is literally 81 times higher than this bar. I mean, if you stacked 81 of these slivers, you would get to this height. What about 1? Well, first of all, notice that getting one person who is left-handed is literally getting exactly one person who is left-handed out of 2 is literally not 0 or 2, right? So again, the probabilities have to add up to 1, and without the typo, they will. So logically, you can get the third case here, the hardest one, by the process of elimination, right? 1 minus 0.81 minus 0.01 will be whatever is left, because 1 is literally not 0 or 2. So we can use our not principle. Alternately, you could just reason that they've got to add up to 1, so 1 minus the ones you've got is the one you don't got. So if you're feeling lazy, that's the way to do it. On the other hand, if you are a little bit more obsessive compulsive like me, and you want to make sure you didn't make a mistake, figure them all out and then make sure they add up to 1. So how could we figure out the one case? Well, exactly one left-handed person means that you get a left-handed person followed by a right-handed person, or a right-handed person followed by a left-handed person. They're two different possibilities. Altogether, RR, LR, RL, LL. 4 different things that can happen. But unlike our head-tail example, not all equally likely, right? It's not a 50-50 split like the head-tail example where you get a half times a half for everybody. It's a little bit more lopsided. And by the way, of course, there is absolutely no mathematical difference here whatsoever between a 10% chance of getting a left-handed person and a 90% chance of getting a right-handed person versus a loaded coin with a 10% chance of landing head and a 90% chance of landing tail. You just have H instead of R and H instead of, well, you get the idea. So what is the probability that you get a left-handed person followed by a right-handed person? Well, again, the slots are effectively independent. So, another typo. 0.1 times 0.9. Sorry about that. So let me say that right. 0.1 times 0.9, which is 0.09. And then if it's right followed by left, then it's 0.9 followed 0.9 times 0.1. So a lot of typos there. Lose the 0, lose the 0, lose the 0. Somehow this one is right. So 0.9 times 0.1, which is also 0.09, is the probability of right followed by left. Now, or means add if there's no possibility of overlap, right? So on the level of what happens when you pick 2 people, if it's a left followed by a right, then it can't possibly be a right followed by a left. We're good. It could be neither, but it can't be both. So we're good. 0.9 plus 0.9 is 0.18. And then without all these typos, it's, well, here it is. So height 0.18. So 0.81, 0.18, 0.01. And by the way, having worked them all out, you then check to see whether they add up to 1, and clearly they do not, so you discover your typo, right? That's how things work in the real world when you check things, which I obviously did not, right? But in point of fact, it's just a bunch of typos here because I probably didn't double check everything. I probably cut it and pasted a lot. So properly done, 0.81, 0.18, somewhat coincidentally, 0.01. And there they are. And you can see it's even more right skewed. The probability histogram makes very clear that if you pick 2 people, you're probably going to get no left-handed ones. And there's a very slim, literally, chance that you're going to get both left-handed. 1 time, 0.01, 1 time out of 100 that you pick 2. You see what I mean? Probability is the proportion of times things would happen if you repeated. Pick 2, 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 pick 2. 81% of the time they're both going to be right-handed, etc., etc., etc. Now nobody likes thinking about repeating repeats, which is why you're better off thinking of it as the probability that both are right-handed rather than the proportion of times you repeated picking 2 that they'd be both right-handed. But it's the same thing. It's nice to have alternate perspectives because you never know which one's going to be easier to think about. How far can we take this without getting a little further into this than we want to in this course. Well, we don't want to talk about factorials or number of ways in this course, so let's see how far we can take it. What if we pick 3 people at random? Well, then there can be 0 or 1 or 2 or all 3 left-handed. So the only way you're going to get 0 left-handed people, and we still have some lingering typos here, the 0 here, the 0 here, the 0 here. But if we pick 3 people, then the only way you're going to get 0 left-handed people if it's right followed by right followed by right, which is 0.9 times 0.9 times 0.9, which is 0.729. Well, here it is in chart form, and this is height 0.729. What about 3? Well, all 3 have to be left-handed, so 0.1 times 0.1 times 0.1, 0.001. One time out of 1,000 that you pick 3 people, they'll all be left-handed. Very slim, right? So literally you'd have to stack 729 of these to get to this height. Far more likely you're going to get 3 right-handed people than you are that you're going to get 3 left-handed people. What about 1 and 2? Well, exactly one left-handed person, but which one? Might be the first one, might be the second one, might be the third one. Now there's 2 things to note about this. It is going to be the same calculation 3 times. But it is going to be 3 times. So yeah, in the one hand, it doesn't matter which one is left-handed. You'll get the same answer. On the other hand, you will get 3 answers. So this is 0.1 times 0.9 times 0.9, properly done. This is 0.9 times 0.1 times 0.9. And this is 0.9 times 0.9 times 0.1. Let me just pop out my calculator. Whatever order you multiply those in, 0.9 times 0.9 times 0.1, I'm going to get 0.081. So there you are, 0.081 or, well, that or that or that. And again, if the first person is the only left-handed one, then it could not possibly be the case that the second person was the only left-handed one, etc., etc., etc. So on the level of what happens when you pick 3, there is no possibility of overlap, right? Satisfying this condition means you can't possibly satisfy this, and so on. Or means add if you can't be both. So it's 081 plus 081 plus 081. Well, it's the same number, right? So really it comes down to how many times you're going to be adding it to itself. So you could reason that way at the beginning. Once you understand that it is the same answer regardless of which one is the left-handed one, then it really comes down to how many of them there are going to be. So it's 0 at 1 in any case. But the first person could be, the left-handed person could be the first one, or the second one, or the third one. So there's going to be 3 of them. You don't actually have to write them out to see that, right? You can just cut to the chase. Without the typos, 0.1 times 0.9 times 0.9 added to itself 3 times. 0.243. And here it is. And here it is. So the probability that you get exactly one left-handed person when you pick 3, 0.243. Call it what, about a third of this height, more or less? Now, reverse everything I just said. The R's become L's, the L's become R's, and you've got the probability of 2 left-handed people. Let's do it a little faster. Now, bear in mind, if you've got the other 3, you can do 1 minus and figure out this one by the process of elimination. But if you're going to have typos, like I do, then it never hurts to figure them all out and make sure they add up to 1. So, reverse everything I just said. The only right-handed person, 2 left-handed, the only right-handed person could be the first one, or the second one, or the third one. And clearly 2 L's times an R, as it were, is going to be the same number regardless of what order you multiply them in. So it's going to be the same calculation added to itself 3 times. Calculation times 3. 2 L's and an R. 2 0.1s, and a 0.9, without the typos, miraculously. So what I have here is technically the first one, but it doesn't matter what order I multiply them in. 0.9 times 0.1 times 0.1 is 0.009. Multiplied by 3 is 027. So there you are. It's 27 times more likely that you're going to get 2 left-handed people than that you're going to get 3. And it's, what, on the order of 10 times less likely than getting 1. So you've literally got to add this sliver to itself 27 times to get to this height. You've got to add it to itself 24-ish times to get to this height, and so on and so on. Incredibly left skewed. The picture makes it very clear that if you pick 3 people, it's highly unlikely you're going to get a lot of left-handed ones, and it's highly likely you're going to get a few number of left-handed ones, right? Very right skewed. 3 doesn't happen very often, but it's comparatively far away from the majority of the substance. What about 4? 4 is about as far as we could go without getting into sophisticated probability principles, so let's reason our way through this. Well, again, notice, I didn't do 2. Oh, okay, I didn't mean to do 2. I'll do it verbally. And I've still got some lingering typos with these zeros here, so sorry about that. I'll fix it in post. So, and I'm missing an R too. It's one of those days, isn't it? But if you pick 4 people at random, of course, then the only way you're going to get 0 right-handed ones is R, 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 R. Right, right, right. First is right, and second is right, and third is right, and fourth is right. So 0.9 times 0.9 times 0.9 times 0.9, which is 6561. 0.6561 probability of 0 left-handed people. Even yet, 0 is going down, but even so far, it is still the majority possibility, right? It's not only bigger than any of the others, but it's more than a half in and of itself. That would eventually disappear if we kept going, but for a while, it's still going to be the most likely possibility. Till we get to 10 at least. So 0.9 times 0.9 times 0.9 times 0.9, 0.6561. So that's the height of this bar, 0.6561. Exactly 4, well, left, 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 left. So 0.1 times 0.1 times 0.1 times 0.1, 0.0001, 1/10,000th. So you literally have to add, you literally have to stack this 6561 times, 6,000-ish times to get to the other height. Exactly 0 left-handed people is magnitudes more likely than exactly 4 left-handed people. Highly, highly unlikely that if you pick 4 people at random, all 4 of them will be left-handed. Still, anything is possible. Probability being what it is, there is either a very slim chance that all 4 will be left-handed, or 1 out of 10,000 of the time that you pick 4 people, they will all be left-handed. It's all in how you look at it, right? So, what about the middle possibilities? Well, again, we don't want to beat it to death. We could if we wanted. The probability of exactly 1 left-handed person, well, left followed by 3 right, or R, L, R, R, or R, R, L, R, or R, 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 L. It's enough to say that the only left-handed person could be in one of 4 slots. It'll be the same calculation, but I'm going to be adding it to itself 4 times, right? So properly done without the leading zeros, 0.1 times 0.1, well, theoretically, if the first one were the left-handed one, it doesn't matter what order you multiply, of course, but for tracking purposes, it would be 0.1 times 0.9 times 0.9 times 0.9. But again, regardless of what order you multiply them in, you're going to get the same number. And while I'm here, 0.1 times 0.9 cubed is 0.729. And then if you add it to itself 4 times, which is what we mean by times 4, then we get 2916. Is that what I got? What happened? Okay, another typo. But it is right in the chart above. So here you go. Lots of typos on this. Sorry about that. It's probably a rush job. I probably fat-fingered the 8 instead of the 1, which is quite an achievement when you think about it, regardless of which way I'm doing it here. But 2916, it's right up here. This is a typo. What's one more at this point? So 2916. At the other end of things, 3 left-handed people means that the only right-handed one could be the first one or the second one or the third one or the fourth one. So it's going to be the same calculation 4 times, right? Multiply 3 L's and an R, as it were. 0.1 times well, strictly speaking, what I've got pictured here is the one I've got pictured here, right? So 0.1 times 0.1 times 0.1 times 0.9. 0.1 cubed times 0.9 is 0.0009 when you get past the scientific notation on the calculator. 0.0009 multiplied by 4, of course, is 0036. 9 times 4 is 36. So that one's actually right, and there it is. Now, as invisible as the 0036 is, bear in mind this one is 36 times less high. So very right skewed. If you pick 4 people, you're far more likely to get 0 or 1 left-handed people, and it's comparatively unlikely that you're going to get 2 or 3 or 4, right? Oh, by the way, the 2 we figure out by the process of elimination here, right? Because it's starting to get complicated. So what do these add up to? Well, they add up to 9514. Not these, of course, because there's a typo, but this and this. And this isn't going to work, is it? Wow, it did. So if we add up those, we get 9514. And then 1 minus is the remaining possibility, 0486. Now, if you do want to double check it, we could reason this way. But let me add at this point, it is starting to get complicated. You see, all or nothing, there's only one way that can happen. One different from the others is relatively different, right? Relatively easy. The odd man out could be in one of 4 slots, or however many slots you've got. But then when you start to get to the middles, you've got to start thinking of number of ways things can happen. And let me just say that although we could do that, it takes us too far afield in this course. It's combinatorics. How many sequences are there with 2 R's and 2 L's? Well, again, we don't want to get into that. We don't want to get into factorials. We don't want to get into combinations in a course like this. You may or may not have seen them before. So let's think it through logically. How many sequences can we make of R's and L's here? Well, there's 2 things that can happen in the first slot, times 2 that can happen in the second, times 2 in the third, times 2 in the fourth. So there's 16 possible sequences of L's and R's here, right? We have accounted for 1, 2, 3, 4, 5, 6, 7, 8, 9 with the extra R, 10 of them, right? So out of 16 sequences, we've used 10. There's only one thing left, which is 2 of each. So there must logically be 16 minus 10 of those, 6 of them. So let's think that through. Any particular one of them would be 2.9s and 2.1s, right? 0.9 squared times 0.1 squared. So 0081. And then logically, I'm going to add that to itself 6 times. So 0081 times 6, and sure enough, that's 0486. Still not convinced? You could theoretically list them all off. I have not done so, so you've got to pay close attention here. The L's could come first, L, L, R, R, or vice versa, R, R, L, L. Or you could alternate, R, L, R, L, or vice versa, L, R, L, R. What's missing? The 2 that people are likely to forget are back to front, L, R, R, L, R, L, L, R. So R's first, L's first, alternate, alternate the other way, put the L's in the middle, put the R's in the middle. 6 of them, sure enough. But it is starting to get complicated. And if I go to 5, then life is going to start getting ugly, right? I've either got to actually list them all off with 32 possible sequences. That's probably a non-starter. Or I've got to use advanced combinatorics to figure out if I have a sequence of 5 or 6, how many ways can I have 2 R's, etc. And although you may or may not have done that in the past in high school, it is not something we want to get into in this course. For all sorts of reasons, everything we've just done is an intellectual exercise only. It is not practical, right? If you want to know what proportion of people in New York State are left-handed, common sense tells you you are not going to pick 4, right? In a word, it's too jaggedy. When you go from one possibility to the next, there's too much of a jump. Even yet, it's not quite as true as it was, but it's still pretty true, right? When you go from bar to bar, there's still quite a jump. In a word, it's still very jaggedy. It's too random. I mean, look at it. You could get 0, you could get 1. There's a fair chance of either one. It's not very stable, is it? And you could even get 2. You're probably not going to get 3 or 4. So it's too unstable. Small samples are too unstable. So in the real world, you don't poll 4 people and ask them who they're voting for. In the real world, you pick 4,000 people. Why large samples are preferred in the real world to small samples, we will see as we go on, starting in section 7 and 8 and 9. But obviously, I am not making the chart for picking 4,000 people anytime soon. There is a paradox that comes into play here. The larger the sample, the more complicated it becomes to do what I'm doing here. So much so that for a course like this, I'm not going to want to go much beyond 4. If I had a fair coin, I could maybe take it up to 5 because I could evenly divide up the middle 2 remaining possibilities there, 2 and 3. But of course, I have no such symmetry going on here. So I wouldn't necessarily want to even do 5, let alone 6 or 7. So obviously, there's a paradox here. The larger the sample, the more complicated it's going to be to make these charts. But the larger the sample is, the less necessary it is to make these charts, because the charts become very predictable. I don't think I did that in this document, but I'll show you what I mean. There is a second example here that you can check out. It is literally the same as what we just did, except it's I think it's a 20/80 split instead of a 10/90 split. Let's see, where would that be? How to use probability rules to make charts. So in this case, it's a 20/80 split, and it's picking people who may or may not have blue eyes. So 20% of millions of people out there have blue eyes, 80% have non-blue eyes, let's say. Then everything we just did, but with a 20/80 split. And you can see that it plays out pretty much the same way. I'm pretty sure that I do all the details here exactly as I did before. Yes, only it probably doesn't have the typos. So just imagine some typos if it's really going to bother you. So this plays out exactly the way it would for the 10/90 split. The numbers are a little different, and here I've actually put them on the sides. A little more detail than I just did in the actual, written down in the actual thing. But if you jump ahead to samples of size 80, the first thing you notice is that there are a lot of bars, and that you wouldn't want to do that by hand. The probability of 0 people having blue eyes, of 1, of 2, of 3, of 4, of 80 bars later, of 79, of 80. So thought of as individual bars, this is very, very complicated. But then the second thing you notice is that you don't have to think of it as individual bars. because it starts to look, whoops, because it starts, success, to look very familiar, right? So on the one hand, thought of as the kind of exercise we are doing at the moment, it is very, very complicated to find the heights of all those bars. On the other hand, the shape is something that is very, very familiar. We'll put all this together in sections 8 and 9, but a look into our future. Large samples, ironically, are much more predictable than small samples. If you flip a coin 5 times, you don't necessarily know how many heads you're going to get. But if you flip a fair coin, 5,000 times, you've got a pretty good idea what's going to happen. You may not know exactly, but it's safe to say that you're probably going to get close to 2,500 heads. Large samples are much more predictable than small samples because the extreme possibilities have a way of canceling each other out. How that all plays out, we'll see in the middle half of the course. All I'm trying to say is that this is an intellectual exercise for very discrete random variables, by which I mean not that many possibilities to think through. If we're making these by hand, then probably picking 4, people who are left-handed or not, people who have blue eyes or not, coins that are heads or tails, probably about 4 is as far as we want to go if we're doing this by hand. Otherwise, it gets off into too much into number of sequences you can get, and for a course like this, we just don't have to deal with it. So this is as far as we care to compute by hand without advanced probability formulas. Also, this is about as far as I think I want to go for this first video. It's now clocking in at 1 hour and 1 minute, so I'll pick it up in the next section. Section 5 is again one of our longer sections, the last of our really long sections, I think. And I am taking it kind of slow because why not? We don't have to worry about class time. So there are 3 main points going on in section 5. Just for future references, we've just covered point number 1. Section 5, point number 1, how to use the probability rules from the last section to make charts and, if you like, pictures for random variables. How to find the probability distribution of a random variable using, this is the probability distribution, the way the probability is distributed for a random variable, using our and or rules from the previous section. That's why the last section was practical. Number 2 will be the center of these pictures, and number 3 will be the spread of these pictures. It always comes back to the same 2 ideas. So now that we can produce such pictures, or having just been given some probability distribution in the statement of the problem, we'll now talk about what we can do with these, whether we found them ourselves or whether we've just been given them in the problem. We'll talk about some of the things you can actually compute from these charts, and that will be in the next video, part B of section 5.